So first of all, I want to thank the organizers for inviting me to speak here and share my experiences both as a user and then also as my insights from within FAIRmat and the developments I've been leading. So I will start with a little bit of scientific science and the background of my latest NOMAD dataset publication, which is 10 electron count rule for the binding of adsorbates on single atom alloy catalysts. And this work I've been doing during my last postdoctoral stay as a Alexander von Humboldt Fellow at the UCL and University of Cambridge with Angelos Michailidis and Mikhail Stamatakis. First of all, you might wonder, what are single atom alloys? These are a special class of metallic alloy surfaces in which a transition metal dopant is atomically dispersed in a more inert coinage metal host metal, such as copper, silver, or gold. These surfaces have been shown to be very promising for hydrogenation reactions, as well as dehydrogenation reactions and exhaust catalysis. The advantages that they have over their pure transition metal counterparts are a very much increased selectivity, sometimes also increased activity, and a higher poisoning resistance, for example, against CO. Of course, it's also an advantage if you have to use some of these very expensive late transition metals like rhodium or ruthenium, that you don't have to use a lot of it, but you have a high atom efficiency because you only need very few atoms at the surface. So, but next is the question, how do we decide which element composition, which element combination we want to go for a specific reaction? And there are a couple of rules that can help us find a suitable catalyst candidate. And one of the most important one is the Sabatier principle, which tells us if we want to have a material with a very high catalytic activity, it should have an intermediate binding strength. The binding of adsorbates shouldn't be too weak, because then they would not adsorb at the surface at all and no reaction is possible on the surface. But it should also not be too strong, because then we would get poisoning of, because the products wouldn't want to leave the surface. So in between there exists a sweet spot where we get just, when we have the right binding strength, we get a very high catalytic activity of a surface. And then the question is, how do we know this binding strength? And we actually don't, as a first approximation, have to calculate adsorption energies on all of these different surfaces, but there is the so-called D-band model, which says that the adsorption energy of an adsorbate is kind of a linear function of the D-band center of that surface. So, and this leads to the fact that the adsorption energies, if you move through the periodic table from zirconium, a 4D transition metal with very few electrons and a very high lying D-band center, that as you go through the periodic table, you get a kind of monotonic decrease of the adsorption energy, or weakening of the adsorption energy. And because of this D-band model and the fact that all these adsorption energies on metal surfaces are a function of the D-band center, we have also these so-called scaling relationships, which make the screening of lots of surfaces easier, theoretically. And then there are, of course, also now newer machine learning approaches which can predict adsorption energies, for example, on a number of descriptors of the surface. So what about now our single atom alloys? If we look at the D-band center here, I plotted the D-band center of pure transition metal surfaces, we see that for the single atom alloys here, I plot the silver-based single atom alloys, so that means we have the silver host and these dopants as single atoms dispersed on the surface. We see that the trend for the d-band center of these dopant atoms is kind of similar-ish to the pure surface d-band centers. So what we would expect now is for these single atom alloys that they also show similar linear trends for absorption energy as we go through the periodic table. So here I show as an example the absorption of a nitrogen atom on one of these surfaces, and what we expected initially would be some kind of linear trend. But what we actually observed was a very surprising U-shape for the trends going through the periodic table here, with the strongest absorption energy for one of the late transition metals, here technetium in this case, and weaker absorption energies to both sides of this row, of the 4D row of the transition metal. This is not only, we didn't only observe this for silver, but also for copper and gold. These curves looked almost identical. And also, if we go to the heavier 5D transition metal dopants, we see that all these curves have a very similar shape. And this goes even further. If we go to other adsorbates from oxygen up to hydrogen, we see that on all these different surfaces, there is this characteristic U-shape of the absorption energy trends across the periodic table. And furthermore, what we also observed is not that they only have a U-shape, but that actually the minimum of this curve here moves over, and so the dopant with the strongest absorption energy moves towards elements with fewer electrons if the adsorbate has more electrons. And this is kind of unexpected if you come from pure transition metals and the paradigm of the d-band model. But then on the other hand, it reminded us of some undergraduate chemistry for molecular complexes. So we thought, well, maybe it was already postulated that this dopant atom did not really mix so much the orbitals, so it didn't really form bands with the surrounding host matrix. So we thought, well, probably we should look at this as a molecular complex, and what if we could design a molecular orbital diagram? So here you see on the left-hand side, you see the d orbitals, the 5 d orbitals of the dopant metal, and on the right-hand, for simplicity, just the 1s of the hydrogen adsorbate. We can form a linear combination in the specific symmetry group of the dz squared orbital with the 1s of the hydrogen and form a bonding sigma state at the bottom and an antibonding sigma star there. And in the case of hydrogen adsorption, the other 4d orbitals do not bind so strongly, so do not form binding interactions and are thus non-bonding. So if we now look at the number of electrons we can put in these binding and non-binding orbitals, we see that we can put up to 10 electrons here before we start to populate an antibonding orbital, which would destabilize the adsorbate bond. So we went further and looked at the electronic structure of these surfaces with the help of the Lobster software also, which allowed us to do some bonding analysis of the different orbital combinations. And what we found was indeed this confirmed our initial very simple MO model that we just draw on pen and paper. And yes, And furthermore, also for the adsorbates with more electrons, we could see the similar rule. We thought, well, could we extend this 10-electron rule that we found also for more complex molecular adsorbates? And we looked at the adsorption of CO and NO on the single atom alloy surfaces, and what we found was indeed, if we assume that CO brings 2 electrons to the metal adsorbate bond, then we can predict that ruthenium, a D8 metal, binds most strongly to CO. And in line with this, NO has 1 more electron. It's actually a radical, and so the maximum shifts to technetium here for the 4D row. Of course, this rule has limitations because we assume that a covalent bond is formed. That means that if we look at other adsorbates, as for example water or ammonia, which do not really form a covalent bond, but where the electrostatic interactions are more strongly dominate, then we see that we don't get this U shape as we get for the covalently bonded adsorbates, but we get more a linear trend, which kind of also correlates with the beta charge of the dopant. Okay, so this, hello? Yeah, so this, with this, I want to summarize the scientific part and background of this NOMAD upload, and I hope I could show you that these single-atom alloy surfaces are very special class, which do not behave like traditional metals, but more like molecular complexes, and they show thus very different binding trends for adsorbates compared to the pure transition metal surfaces. And we have this electron rule with which we can predict now which dopant would bind an adsorbate most strongly. Now I want to draw the line back to NOMAD and what I think are the advantages of sharing computational data in NOMAD. I think first of all I want to say it's really, really easy to do. All you need to do is to zip the computational folders together and all at once you can just upload them and they will be passed by NOMAD into different entries. NOMAD will automatically detect which is the computational output file and generate the structures. Furthermore, you can make it more understandable if you also include, for example, Jupyter notebooks, which generate the plots that you, for example, have used in the publication. You can also add an MD file to add more explanation and background to each upload. And now there's also the option to add workflows and combine different DFT calculations to, for example, have the reaction energy calculated directly in NOMAD as well. So this is the end of the first part about the theory data. If there are any questions at this point, I'm already happy to take them. But if not, I will... Oh, there's one. Brilliant. Yes. Yeah, you can just upload it. Yes.
It has to be the root folder, of course. It's similar to what GitHub and whatnot's doing.
Yeah. Okay, so next about the work that I've been doing during the last year when, as I was part of FAIRmat. And now, as it is already possible to fairly share computational data to a large extent, but there is a big problem with experimental data, as we already also heard yesterday in the talks. So what's also especially true for catalysis research, that there is lots of manual work still involved, especially during the synthesis and formation of the catalyst preparation. There are lots of handwritten notes. And when we go to the physicochemical analysis, there are lots of proprietary data formats, which are difficult to handle if you want to share them in a fair way. There are also lots of self-built setups which lack even more of community standards. The most researchers probably collect their data or aggregate their data manually in Excel tables, and there are only very few automated reactors which might already produce an HDF5 file, for example. And I think because of all these difficulties with sharing the data, there are actually no general overarching databases for experimental heterogeneous catalysis. There is one very specialized one for just methane oxidation reactions, but otherwise, there is none. And so with my work, I want to help make NOMAD the place to upload experimental heterogeneous catalysis data. And what I've been doing was developing different schemas for catalyst sample entries as well as for the catalytic functional tests, the activity tests, which are developed in a plugin. I have started by using different example data sets ranging for different types of chemistry, ranging from oxidation catalysis, CO hydrogenation, methanol hydrogenation, and ammonia decomposition. And what these schemas that I've developed in the catalysis plugin do is that they take a table, for example, CSV file or Excel file, or in one case of ammonia decomposition where we have an automated reactor, also an HDF5 file, and it automatically puts all the information from the different columns into the quantities and subsections in the schema. And the entry then also shows nice automatically generated plots, as I will show you here on the next slide. One example. So this is one for ammonia decomposition, where we just have to upload one this HDF5 file, and then all the information from that is read into the entry. And these plots are generated here for different pre-treatment, for example. You can directly see the temperature program that was performed. Yeah, this is another example for the oxidation catalysis, where the data source you can upload an Excel file. And with the tabular parser that's available in NOMAD, it's also easily possible to generate lots of data entries at the same time, where you just have to specify the file that contains the data for one specific measurement as in one column. Yes. Oh yeah, and then there are more plots that show you, for example, conversion over time, or also selectivity versus conversion plots for this single measurement. Okay, then I think one important part to ensure also the future understandability of these schemas is to link this with community-wide understanding of the meaning of those terms. So what I did is to link each quantity and section name to a definition because in an ontology or vocabulary, and because there is no really general enough ontology for catalysis research, we have started to work together with the NFDI for CAT, which generated a voc4cat vocabulary, or a vocabulary called voc4cat, and we've contributed a lot of the vocabulary already that I'm using in these NOMAD schemas. Okay, and then the next part is, once you have the data there, you can really, and have it in a structured format, in a machine-readable way, we can really make use of it and have nice overviews of all the data that's there and search much easier. So here, for example, at the top, you see you could select which reaction you might be interested in if you are looking for specific kinds of data. You can specify the reaction name or the name of the reactants or products. Then there's a next section where you could specify more information about the catalyst if you are interested in a specific elemental composition or some specific preparation method. And you see at the same time you get a nice overview of what's there, but you can also use this to filter down the entries you are interested in. And then below that there is a section for the reaction conditions where you can see which concentrations, for example, the reagents have been fed into the catalytic test, can specify pressure and also other quantities like weight, hourly space, velocity. And of course, the temperature range, which is here. And you can use these plots at the same time to get an overview and also to zoom in and filter down the entries you are interested in. And then you get really also to the core of the catalytic information, which are conversion and selectivity values, and can go and analyze deeper the trends that you see. So, I think, I don't know, I have a short video I could show, if there's one more minute. Yeah, right. How is it? Oh, sorry. How do I know? Now. Okay, so now it starts. You can hear, for example, I selected oxidation of propane as a filter, and then you can scroll down and see all the conditions that have been applied. And these new scatter plots, you can interactively change what you see in them. So you can, for example, change the products or adjust it to the specific reaction you're interested in. Here, because we are looking at oxidation, there's of course no CO conversion, but an oxygen conversion. So you can change the name of the reactant to molecular oxygen. And then you will see what data is there. And here is, as a marker, the preparation method of the catalyst has been used. And you can directly see which is the best preparation method, which gives you highest selectivities, or in this case, because maybe you actually don't want CO2, which so you see that this precipitation gives actually in this case a very bad result because it leads to the complete oxidation. Whereas on the other side you see acetic acid selectivity, so you see that maybe you want a high selectivity towards this partially oxidized product. Yes, and with this I want to conclude and say that although it might seem daunting at first, everyone can start to make their data more fair, even if it's at the in the first instant just publishing basically the information of an Excel sheet. And step by step we can move to make it more fair and include more raw data. And so, and once you have this structured machine-readable data, you can really, it can be very useful both for just giving you a good overview over the data, and of course later on we hope that with machine learning applications and AI it can lead to faster development of better catalysts. Yes, and with that I'm at my end and I'm happy to take any questions.